Alright, today let's talk about something more modern. Let's talk about object detection. This is part of computer vision. Let me write that down. Computer vision. So, object detection is part of computer vision, which itself is just, as it seems, allowing a computer to see. I can draw an eye, see, computer vision. So how can you make a computer see? That is the field of computer vision, and that's what researchers are trying to solve. And object detection is just one part of this. So what is object detection? So object detection is a field of computer vision where computers are trained to detect objects in an image. So let's say I draw something here. Let's say I draw, it's a person and behind is Mount Fuji. I cannot draw Mount Fuji, but I'll try my best. Object detection would say, let's try to find a box where you contain the person and a box where you contain the mountain. And the computer would know, this is, let's say, a human, let's say 95% confidence, and then this is a mountain with, let's say, 80% confidence. So that's the purpose of object detection. You're trying to detect objects in an image. And there are multiple ways, multiple neural networks, multiple algorithms to find out how this works. So today I'll be walking through the most traditional method of doing so. Nowadays we have a lot of new deep learning based architectures. Those are a lot more efficient, but today I'll go through the most foundational ones that have built up traditional models like RCNN. So I'm taking reference from the RCNN model. This was discovered in 2014, I think, and it's quite influential. So what's an RCNN? Let's go back to the image we had just now with a person and the Mount Fuji. An RCNN has three parts. One is called region proposal, where you are trying to propose regions of interest. Next, you have to classify the regions that are proposed. And lastly, you have to get conclusions, basically. Just conclude from the regions what is detected, what is not. Let's start with the first one. So region proposal uses multiple traditional computer vision techniques, and basically what it tries to do is to get interesting regions. There is no criteria for interesting. Some algorithms use the colors, the edges, the things inside the image, but all in all, it will just try to regionize and get bounding boxes for a lot of different things in the image. So let's say add more things like clouds, let's say add a bird. I can't draw a bird, but let's say we have a couple of things in the image. A region proposal network would just draw boxes around all of these, and in fact they might even overdraw. They might draw two boxes over a single image. They might draw one horizontal, one vertical. Needless to say, region proposal produces a lot of regions, some of which may be redundant, but they're just generating a lot at once. Next, with each of these regions, we want to classify them. And classifying regions is done using another neural network. Normally, it's a CNN, or a convolutional neural network, which is a type of neural network that's really, really good at classifying images. So once you get the regions, you crop that part out and then you send it into the CNN. Once you send it into the CNN, then it will be very good at classifying that part of the image. And so now we have labels for each of these parts. We have classified each of these regions. So let's say they might think, maybe it's a plane, it's not a bird. Then these are all the same part of cloud. They might say, this looks like a hill, but this looks like a mountain. And maybe they say, these two are just a person. Hooray. So now we have labels for each of these regions. So what's the last part? Well, we have just a bit too many labels, a bit too many regions. How do we know what's important, and how do we know what's not important? There's a technique we call non-maximum suppression. Non-maximum suppression. And it has two main factors. One is it checks how much of the box is overlapping, and second, it checks how confident the prediction is. So let's just scroll down here. Let's use this mountain for example. Let's say I have a mountain, and then I have two bounding boxes where I have one like this and one like this. This is just for illustration. Let's say both are considered mountain. However, one of them, the big one, has a 95% confidence, while the other one has a 60% confidence. The model looks out firstly for the overlap. So it sees that, this area in the center is overlapping quite a lot. Let's say it overlaps about 50% of the area. In actuality, they use this thing called IOU, intersection over union. We don't talk about that, but put it there for notice. So first it checks for the overlap. If there's a very significant overlap, let's say in the case of the person one here, there's a lot of overlap, they will know that, it's most likely the same thing. Next, it also checks the accuracy. So let's say the accuracy, or like confidence. Where is it? Confidence. So it checks the confidence of the model and say, this is 95%. It's a lot more likely to be accurate, and so it will choose this one. It will delete the less important one. It will choose the more important part of the model, and so it will delete the less important, probably misclassified box, and then all that remains is this high confidence and mostly unoverlapped bounding box. And so if you repeat this for all the rest of the things in the image, you would probably get a much cleaner and hopefully more accurate regions and objects. And this is the final output. You see again, it's just like the top. You have labels for each of them, and you probably have some confidences in the form of the outputs from the classifying regions part. So that brings us to how we have classified images. We have gone from just one image without anything all the way to having labels and object boundaries. So yeah, hopefully this gives you a brief understanding of the object detection process, how it goes from image to bounding box detection. Yeah, thanks.